Okay, here's video 1 of chapter 2. Chapter 2 is on atoms, molecules, and ions. So here the atomic theory of matter, it's also called Dalton's atomic theory oftentimes. Here are kind of the 4 main points of his theory. Each element is composed of extremely small particles called atoms. Those are the building blocks. All atoms of a given element are identical to one another in mass and other properties, but the atoms of one element are different from the atoms of all other elements. We'll see how the beginning of that is a little bit different now. C, atoms of an element are not changed into atoms of a different element by chemical reactions. Atoms are neither created nor destroyed in chemical reactions. That's the law of conservation of matter. So all of the atoms at the beginning are still present at the end. They've just been rearranged. And then compounds are formed when atoms of more than one element combine. A given compound always has the same relative number and types of atoms. That's the law of constant composition. Like water, for example, will always be 2 H's to 1 O. It has a constant composition if it's a compound. So here are the main 4 experiments that led to our understanding of the atom. A and B, the first 2 experiments, mostly were discovering the electron, the fact that it was present, it was negatively charged. And then C, Rutherford's gold foil experiment was really a big changing point for the understanding of the atom. What his experiment discovered was that there is a nucleus in the atom, that there was a dense region in the center of the atom, and then the rest of the atom really was almost empty space. So what we now know is that an atom, if you were to take an atom and think about the nucleus the size of a grape, and then you go out a mile in every direction, that would give you the scale of an atom. A nucleus is very tiny, but that's where most of its mass is and where its density is. We'll talk more about the structure of the atom as we go. So the 3 particles are the protons, neutrons, and electrons. Protons are positive 1 charge and a mass of around 1 AMU, which AMU stands for atomic mass unit. A neutron is neutral and also has a mass of right around 1 AMU. So do you notice these 2 are almost identical in mass? The electron is a negative 1 charge and it has a super tiny mass, 5 times 10 to the negative 4th. So his mass is very insignificant compared to the proton and the neutron's mass. So what we want to know is that the charge of a proton cancels out the charge of an electron. So if an atom is neutral, these 2 particles will be equal. 10 protons means you also have 10 electrons. The mass is only dependent on protons and neutrons. So the electrons, we just say their mass is negligible. It's kind of like getting on a scale and then pulling a piece of hair out and getting on the scale again. You did lose mass. It just wasn't a noticeable amount of mass. So the mass of electron is insignificant for us. So we say if we take a proton and a neutron, each one has a mass of about 1 AMU. So here if we look at atoms, for example, carbon on the periodic table, carbon looks like this right here on the periodic table, where it has a number above it, which is 6. The numbers above are called atomic numbers. They tell you the number of protons in that atom, and that is different for every single atom. So it's the distinguishing factor between all atoms. So if you have 6 protons, you're automatically carbon, no questions. Your mass number is at the bottom of the square. The mass number tells you the total number of protons and neutrons added together. So it's the sum of those. You can see different elements can be written in different ways. Like it can just be plain old carbon, which would be a C. Or sometimes the element with the mass up top and the atomic number at the bottom. Or just the atom and the mass and the atom and the mass. We'll see that when we talk about isotopes as well. The mass number can help us figure out how many neutrons, because if you think about carbon, automatically he has 6 protons because that's the atomic number. Then we also know the mass is 12. So if the mass is 12, we know that the protons and neutrons have to add up to 12. If there's 6 protons, there must also be 6 neutrons. So we determine that through mass. And then if the atom is neutral, which unless you're shown a negative or a positive, the atom is assumed to be neutral, which means your electrons have to be equal to your protons, so 6 and 6. So let's practice again. If we look at fluorine, once again on the periodic table, here's what fluorine looks like, 9 and 18.99. Protons automatically 9 because of the atomic number. If it's neutral, the electrons are equal to the protons, so also 9. And then we look at the mass. So if we're looking at number of neutrons, we just round the mass to the whole number. So if this rounds to 19, I know that the protons and the neutrons have to add up to 19. There's 9 protons, so there must be 10 neutrons. Isotopes are where you have different versions of the same atom. So for example, you can have multiple carbon atoms found in nature. They all have 6 protons. That can't change. But their masses are different. Their mass is different because they have a different number of neutrons. And we'll see an example. So carbon 12 and carbon 14, they differ by 2 neutrons. To determine the average weight of an isotope, what you do is you are given the percentage found in nature. It's also called the relative abundance. So here it tells you that chlorine 35 and chlorine 37 both exist in nature. 75% of the atoms out there are chlorine 35 and 24% are chlorine 37. And then you're given their exact masses. So what you do is normally for an average, you would just add and divide by 2. But what we do is we take into account which one is the most common isotope. So you do the same thing every time. You take your percentage, you divide by 100 to get it to a decimal form. So that's where the 0.7578 came from. And you multiply it by its given mass, which was 34.969, okay? Then you do the same thing for the other isotope. You take the 24%, you divide by 100 to get the decimal, and you multiply it by its given mass, which was 36. And then you add these things together, and then you get the average here as 35.453. I went with the same sig figs as the original masses were given. Silicon has 3 isotopes, silicon 28, 29, and 30. So here you have 3 different isotopes available. You do the same thing. Take the percentage, divide by 100, multiply by the mass given. Go to the next one. Take the percentage, divide by 100, that's your decimal, times by its mass. And thirdly, you take the last percentage, divide by 100, and multiply by its mass. You add them together to get your average mass there. If these are real elements, their average mass should match what's on the periodic table. That is what is listed on the table. Okay, the arrangement of the periodic table. The periodic table is arranged by its columns and its rows. So the columns are called groups. Groups are really important because they tell you that atoms in that group have similar properties. So the vertical columns tell you a lot about an atom, and those are called groups. Rows, the horizontal rows, are called periods. They do not tell you as much about what those elements are like. So the groups here are listed, and I'll show you a periodic table here in a second as well. But they can be labeled 1A all the way through 8A, but only a few of them have special names. So we'll see how they're labeled. But 1A is always called alkali metals, 2A alkaline earth metals, the 6A you don't have to know, 7A halogens, and 8A noble gases or rare gases. You can see their elements listed here to help you a little bit too. But we want to be familiar with these 4 group names so that we know who we're talking about immediately. Here's a periodic table I can show that better. So the group numbers are labeled up here. You can say either groups 1 through 8 or 1A through 8A. Both are accepted. So 1A, 2A, and then you skip all these B's. We'll talk about the B's here in a little while, but they are not different groups for us. So 1, 2, and then you jump over here to 3, 4, 5, 6, 7, 8. Different periodic tables are listed, titled differently, but we want to be really aware of this 1 through 8 system here that you see. So these are the alkali metals, group 1, the alkaline earth metals, group 2, The group 7 are the halogens, and group 8 over here are the noble gases. Okay, these in the middle are going to be called transition metals, and they don't differ so much one group from another. We kind of put them all in one category, which we'll talk about those here in a little while. The periods are the horizontal rows. So row 1 is only hydrogen and helium. That's period 1. Period 2 starts with lithium and goes through neon. And then period 3 starts with sodium, etc. So you go down all the way through 7. Some atoms exist as what are called diatomic molecules. Diatomic molecules are atoms that exist in pairs in their elemental state. So there are 7 of them. Oh, 8. Unless I've written one twice. Nope. So here they are. And they always come as pairs when they are found in nature by themselves. So hydrogen and then nitrogen, oxygen, fluorine, chlorine, bromine, chlorine, iodine. The way I like to remember these is they actually make, yeah, I put chlorine there twice. There's only 7 of them. So there's hydrogen, who's out here by himself, over here on the left. The others make a 7 on the periodic table. So nitrogen, oxygen, fluorine, chlorine, bromine, iodine. So there's a total of 7 of them, and we will need to be aware of these. So if I just say oxygen gas, you have to know that that is O2. Once oxygen's in a compound, he does not have to be O2, for example, in water. So chemical formulas show a formula of a compound, and these little numbers are called subscripts, and they tell the number of each type of atom in a compound. So there's different types of formulas that we'll run into. I'll just touch on them here and then we'll be back to them. But a molecular formula indicates the actual number of atoms in a compound. For example, octane. Octane exists as C8H18. That is what the compound actually looks like in real life. An empirical formula is the simplest ratio of atoms. So do you see that you could take C8H18 and simplify? Because 8 and 18 can both be divided by 2. So you could get C2H9. That's called the empirical formula because it is the simplest ratio of that compound. The molecular and empirical can be the same and they can be different. For example, water. Water actually exists as H2O. That is the simplest ratio, 2 to 1. So that's both the molecular and the empirical formula for water. H2O2, it has different ones because the molecular is what you see. 2 H's and 2 O's is really what it exists as. But simplistically, the empirical formula is just HO. It tells you there's 1 hydrogen for every 1 oxygen. Structural formula shows the arrangement of atoms. For example, it looks like this. We'll talk about that a few chapters later.